came up with.
So are there any questions on the homework?
Yes.
Okay. Which one?
It's bad, but it's 2-1. And number 4. It's like part D.
0H.
Yeah.
So let me go back to our notes.
What?
And see, I think we did something similar. No, we did this one here from 1 to 1 plus H. So it's not quite the same, is it?
No, I tried that way.
Okay. All right. Just making sure that we haven't covered that yet. This was 4. So we have position, we want to find the average velocity, which is the slope of the secant line, over the interval, we're looking at part D, part D, over the interval 0 to H.
Oh, just plug H in? Or no?
So what's this going to look like once we're done computing the slope of the secant line here? Will it involve T? Will it involve a number? Will it involve H? What will it involve? It'll involve an H, right? Because we're not given a value for this H. When we're given values like 0 and 3 or 0 and 4, we get a specific number in return when we calculate the slope. But here we just have one number and one variable, more or less. So what we're coming up with the slope of the secant line in this problem is some expression involving H. Again, it's very similar to the one we did in our homework class notes. I believe it was question 5 or question 3, I don't remember. The one we just pulled up from 1 to 1 plus H. Do y'all remember doing that example? So this is similar, except for this, instead of 1 to 1 plus H, this is 0 to 0 plus H, basically, is the only difference here. Right? Does that make sense, that this is like totally similar to that? So if I'm looking at intervals from like 1 to 2, and then 1 to 1.5, in general, I'm looking at intervals from 1 to 1 plus H, where H is just some small step size from 1. But here I'm looking at from 0 to 3 to 4 to 6. Even those are getting further and further apart. From 0 to H, I'm looking at values, I can specify any value of H from 0, and that'll be the distance. So like this is 0 plus 0.1. In this instance, H equals 0.1. So it's kind of the same idea. That we had in that other problem. So slope of the secant line, what form does that take? What does it look like? Difference quotient, or the change in y over the change in x. So we have the function s evaluated at h minus s evaluated at 0 all over h minus 0 or h. So S of h, we get negative 4.9 h squared plus 32h plus 23. And then we're subtracting off our position function at 0, which is 23. And all of that's over h. So there's the slope of our secant line, and we can simplify this by factoring out an h and canceling. So we have negative 4.9h plus 32. So that's the average velocity on that interval. And if you want to go back, we could start here, and if you want to go back and do part A, h equals 3, part B, h equals 4, and h equals 6 in part C. And then we can just plug 3, 4, and 6 into this function, and you're going to get the same result you got in part A, B, and C when you calculated those numerical values, or those slopes. Does that make sense? Do y'all have any questions on that? So it's just a more generic way to look at computing successive secant lines, slopes of secant lines. Any other homework questions? Yeah?
2.3, number 14 and 18.
Let me start a new page. New section.
I honestly don't know why I'm having such a hard time with that.
You said 14 and 18?
Yeah.
Are they similar?
No, mostly 18. I just kind of need to get 14 started.
Okay. So, find the following limit or state that it does not exist. H is approaching 0 and we're dividing through by h. So that at this point we either need to do something algebraically to try to simplify that, or we have to default to the stuff we're going to look at in 2.4. So what would we do here?
Would it be the conjugate?
So would we need to multiply through by the conjugate? We could do that, right? There's nothing wrong with multiplying through by this quantity squared plus 9. But remember, when we have something times its conjugate, it always turns into the difference of squares. So then we would have 3 plus h squared squared minus 81.
Would we just expand that and like we can't really take out an h because there's no h in front of the 9?
Yeah.
But
So.
all the 9 cancel out because it'd be.
Right.
I see it. And I'm
Yeah.
like, can we just do 18?
Well, let's see this. This one here, all you have to do is expand the binomial. And then those 9s will cancel away. Similar to what we just did. Now we have a factor of h in the numerator that can come out. Oops. Uh, 6 plus h. So that would be, what? 6. H approaches 0. So that's 6 plus 0. So, you know, I recognize that we do have a lot of different methods to solve these limits that don't evaluate initially. And so that's part of doing the homework is, you know, when you look at some of these, you probably have like 2 or 3 things you're thinking of in your head. Which one should I do? It's really just a trial and error until you start to recognize patterns. You can eliminate some of the other methods. Like, I definitely wouldn't do such and such for this problem, you know, and that occurs after you've seen a few. But a lot of times at first, initially, some of these aren't totally obvious as to what you should do. So here, see the dash T? We're going to use technology to help us through this. Oh, it's a multiple part.
Mostly C. I honestly got it right and I don't know why, so I just...
Part C.
Yeah.
So let me just kind of try to annotate as we go. Is the statement true for all x? Choose the correct answer below. So again, to verify this is true, we're just going to graph this. So we're going to graph the negative absolute value of x as one function, x sine of x over 2 as another function, and graph the third function as the absolute value of x. So we're just going to look at the graph to verify, is that true? And for all x not 0, that's kind of leading us into the fact that we're going to be looking at a limit as x approaches 0. Yeah?
It's 2 over x, not x over 2.
Oh, 2 over x, yeah, thank you. So we would look at the graph that, please let me see how to do this here. I'm going to say it's true. And that's just building off of our graph in part B. So absolute, negative, absolute, that look like. I don't know, let's just get through this. And then so part C says use the squeeze theorem to evaluate that limit. Oops, I kind of cut it off. So what is that limit? Zero. How do we know that limit is 0?
Would we just plug in 0 for all x's?
For all x's in the inequality that was given to us. So if we know that inequality is true for all x except x not equal to 0, then we just look at the limit on both sides. I guess I should have left some space. Limit here, and the limit here. Remember, the one in the middle is what we're trying to answer. We don't know anything about it. We can't simplify that. We can't conjugate, rationalize anything. But we do know the limits on both ends. So we always have to insert our limit into the inequality that's given to us, and then hope that the endpoints, or these ends here, actually evaluate to the same number. Otherwise, the squeeze theorem isn't helpful to us. So since they both evaluate, we can then say this limit is 0. Right? So this, whatever this is, it's larger than or equal to 0, and it's also less than or equal to 0, so it has to be 0. Therefore, that limit is 0.
So if both sides equal 2, then the limit would be 2.
If both sides were 2, the limit would be 2.
Okay.
Yep. Remember, that's like saying I have a number that's smaller than or equal to 2, but it's also larger than or equal to 2. It has to be 2. So we alluded to this problem, or similar problem last class. If something like this were on the exam, it would be, you would already be given an inequality. You just need to utilize the limit on the inequality to see if you can answer anything about the limit itself. Is that clear? Are there any other questions on that? Any other homework questions? We left off here in 2.4. We're discussing, basically we were just giving an overview of 2.4 and 2.5 is what we were talking about. So 2.4 were limits at infinity, telling us where vertical asymptotes are. 2.5 limits at infinity, which tell us the end behavior where the horizontal asymptotes are. And then the rest of this right here was just discussion about linear polynomials and exponentials. Try to reopen this. Okay. So do y'all have that definition in your printout? Okay. So I know you don't have the figures. I added those just because the definitions do refer to those figures. But so the definition is, what does it mean to say we have an infinite limit? So if the y values grow arbitrarily large for all sufficiently x values sufficiently close to a, then that's what we write. The limit as x approaches a on f of x equals to infinity. So again, what that's meaning is as x gets closer and closer to a, the finite number a, 2, 5, negative 12, the y values continue to grow in the positive direction without bound. Similarly, if the y values grow in the negative direction without bound, we say the limit as x approaches a on f of x is negative infinity. Now, in both cases, as we stated earlier, in both cases, the limit does not exist. But if we do come up to a problem where these things are applicable, we need to write infinity or negative infinity. It's a lot more descriptive than just saying the limit doesn't exist, right? Because if we say the limit doesn't exist, there might be a jump in the graph, there might be an asymptote. So when we write this, the limit doesn't exist, but we are specifying, we're giving ourselves more information about what's happening on the function as we get closer and closer to a. So we do need to write these out as infinity or negative infinity. So 2.4a, as we approach a from the right or the left, the y values grow without bound. 2.4b, as we approach a, the y values grow in the negative direction without bound. So sort of just to add a visual to the words that we're defining there. And then you have a definition for one-sided infinite limits, which reads much the same as the previous definition, except for when we define a one-sided limit, we're always specifying, are those x values larger than a to the right of a, or are the x values smaller than a to the left of a? So it's the exact same definition, except for we're modifying where x is in relation to a. So as we, for instance, for this one here, if x approaches a from the right, on this function, it equals to infinity. That just means as we get closer and closer to a from the right-hand side of a, or values larger than a, the y values grow without bound. If we get closer and closer to a from the right, and the y values are negative infinity, that's illustrated there as well. And so all of these scenarios are illustrated with these four figures. Just again to give you a visual sense of what that definition is addressing. So as we discussed, in any of these situations, whichever one we're talking about, it's going to vary from function to function depending on what you're approaching to. But we're always talking about a vertical asymptote. That's the only way that the y values can grow without bound as we get closer and closer to some number. Is that conceptually okay? Do y'all have any questions or need clarity on any of that? Okay, so let's we'll look at the limit on this stuff in a moment, but just to kind of maybe refresh our memories on when we see functions like this, from an algebraic or a maybe even a pre-calc sense, what do we know about that particular function, 5 plus x over x? Okay, yeah, so we should start with the domain of that function. The domain are all real numbers except for 0. And then we ask ourselves, does that function simplify? Because if it simplifies, the factors that get marked out or cancel, those are corresponding to wholes. The factors that don't correspond to vertical asymptotes, right? So what happens at x equal to 0 on this function 5 plus x over x? It's undefined, okay? So what kind of undefined is it? Is it a whole?
Vertical asymptote.
It's a vertical asymptote because that factor of x doesn't go away. So there's a vertical asymptote at x equals to 0. I hope you all aren't in the habit of canceling that x, because that doesn't cancel. This is 5 over x plus x over x. So it does equal 1 here, but it doesn't equal 1 over here because we still have 5 divided by that. So don't just cancel those x's out. Of course, if they're separated with multiplication, then you could. But things that are separated by addition and subtraction, you can't divide away. So, that information we can obtain just by looking at a function, maybe even simplifying it if it does simplify. And so then we say, well, what does it look like? If I know I have this vertical asymptote here, what does the rest of the graph look like? How do we determine that? Or we can ask the question now, how does the function look when we're close to the asymptote? Is it up here like this? Is it doing this? Is it down here? So On either side of that asymptote, where's the function? What is it doing? From an algebra approach, how would we determine that?
Plugging values.
Yeah, we just plugged values in, right? We said, okay, well, what if, I don't know, what if x were 1? Well, then we have 6 over 1, which is 6. So then that would give us this point here. You know, what if x were a half? Give us this value here, right? So we plugged in those values to determine where's the rest of the function at. Hopefully you remember that. So since we have a point here, it wouldn't be this one. It wouldn't be this one down here, sorry. The rest of our graph is up here. So that graph is approaching the asymptote that way. And then to determine what's happening on the other side, maybe we picked -1. The function evaluated at -1, 5 minus 1, 4 over -1 is -4. So then that tells us on this side of our asymptote, the function is down here. You know, doing whatever, wherever it's going. Vaguely seem familiar? So now when we look at it through a limit process, we're going to say, okay, this function, as we approach 0, we know there's a vertical asymptote there. You have to approach it from either side. Because remember that the vertical asymptotes are, in effect, taking the plane and cutting it. So you have two separate planes, more or less. So as we look at the limit's going to say, as I approach 0 from the right on this function, that the y values are tending towards positive infinity. And as I approach 0 from the left, the y values are tending towards negative infinity. So really, without thinking about where are the other points, what does the graph look like, in one limit statement, you're going to get all of that information. So from calculus then, we're looking at the limit as x approaches 0 from the right. That's going to give us a piece of information, and the limit as x approaches 0 from the left on this function is going to give us another piece of information. And we've already seen visually from an algebra pre-calc approach what those limits should be. But we're going to discuss how do we evaluate that so that we don't have to end up graphing it. So honestly, if you remember in context of 2.3, how we evaluated some limits where factors canceled, that in conjunction with this technique kind of eliminates the need to remember all of that stuff from algebra and pre-calc. Oh, well, what happens if this factor cancels versus what happens if it stays? I mean, you still should remember it, but this is a completely different way to describe the same information. So that's our definition of a vertical asymptote. No longer are we saying a vertical asymptote are zeros of the denominator that are not zeros of the numerator. Now we're saying that if the limit on some function as we approach some finite number a is positive or negative infinity, or from either direction is positive or negative infinity. If any one of those things happens, then the line x equals to a, whatever we're approaching, the line x equals a is a vertical asymptote. So that's how we're defining a vertical asymptote now. If we get a limit that evaluates to infinity, we know there's a vertical asymptote at that value of x we're approaching. So really, to evaluate these limits, what we're looking at is if we have one function divided by another function, well, sorry, we're looking at the limit on that. Let's just say the limit as x approaches a. So if we have this limit we're evaluating, and the limit of the numerator portion, the limit on f of x, is finite. In other words, when we compute this limit, our numerator is coming out to equal some number, positive, negative, doesn't matter. Then what happens with g of x, the limit as x approaches a on g of x, we'll just say equals 0. But again, in the context of a limit, g of x is approaching 0. I left something out because I want to think about that. I want y'all to think about this just in a different way. Okay, so if I compute the limit on this quotient f over g, f is approaching a finite number, but g is approaching 0. What would that mean about this limit, f divided by g? It's undefined in the sense that it's getting closer and closer to what? The denominator is getting closer and closer to 0, but what's the quotient getting closer and closer to?
Positive or negative infinity.
It's getting closer and closer to a positive or a negative infinity, right? So just maybe on your calculator, take some finite number, 20, divided by 10, divided by 20, divided by 1,000, 2,000, 10,000, 100,000. Every time you keep dividing through by, every time you keep dividing through by smaller and smaller numbers, so take 20 divided by 1, 0.1, 0.001, 0.00001. Anytime you have some number divided by another number that's getting smaller and smaller and smaller, the quotient gets larger and larger and larger. So if we have a limit that's evaluating to an infinity, positive or negative, the numerator is finite, the denominator is getting smaller and smaller. All of the other examples we've seen, like that last homework problem we looked at where we're dividing through by h, and h was approaching 0, that wasn't the case because what ended up happening was one of the h's in the numerator divided with an h in the denominator, right? And that gives us a whole. We're explicitly talking about functions that don't reduce. If the numerator approaches some finite number, denominator approaches 0, then the quotient will approach infinity or negative infinity, depending on the values. Is that clear? Because we have seen many, many examples where the denominator is approaching 0, but we were able to evaluate it as a finite number because all of those things were wholes, not asymptotes. And so really then, when we look at these things, I would say hopefully you still have a working knowledge of rational functions determining if something's a whole or a asymptote, at least until you get the hang of this. We know that we're going to be approaching infinity when we approach an asymptote, right? So really the major question here is, what values are we approaching that infinity? In other words, are we growing without bound in the positive direction or in the negative direction? So that's kind of the main issue with these problems. What values is g of x approaching 0 through? Are they positive or are they negative? Right, because we know 0 is neutral, but we can approach 0 through negative values or through positive values. So to kind of see how that unfolds here, going back to the function that we already looked at, we said, well, x equals to 0 is a vertical asymptote. So that can be really, really helpful in these types of cases. So as I'm approaching 0 from the right, what does the numerator approach?
Positive infinity.
The numerator only. So the numerator approaches 5 as x approaches 0. That's not the problem. The denominator approaches what? 0. What values of 0 does it approach through?
Positive.
It's positive values, right? Because we're to the right of 0. So this is not really a universally agreed upon notation. But in the sense that the numerator is fixed at 5, or getting closer and closer to 5 rather, but the denominator is getting smaller and smaller through positive values, we have to know that this part right here is telling us that the overall quotient is approaching infinity, but the sign, we've got a positive 5 over positive, really small positive numbers. So we've got a positive 5 over the positive. So really the signs here are giving us the fact that this is a positive infinity. Some people look at these in a numerical sense, which is fine. You still have to know that, I think when we tend to look at it as one fixed number, like x is approaching 0.00000001, your calculator is going to give you a specific value in return, and a lot of times people have a tendency to just put that value. But you just got to keep getting closer and closer to 0. So just to see what I'm talking about, if you have your calculator out, take 5 and divide it by 0.00001 or something like that. And then what do you get for the value?
Very large number.
Very large number, yeah.
What
Like
happens if you have a
50,000.
negative on top?
Do what?
What happens if you have a negative on top?
So what happens if the numerator were approaching a -5?
Negative.
It would be negative infinity, because we would have then a negative over a positive, which is a negative. So then that would approach negative infinity. So that, I mean, there's really nothing wrong with thinking about this in a numerical sense. It is a different way to evaluate things, but that's 500. So we can just keep going. We see those numbers as we get closer and closer to 0. Those numbers getting larger and larger and larger. Just if you, I just want to remind you, if you are going to look at these in a numerical sense, don't just write down the single value your calculator gives you, because the denominator has to approach 0. In other words, you have to keep making that smaller and smaller and smaller. Is that clear, or not really? So a very similar thing here for the limit as we approach 0 from the left. Again, the numerator is approaching 5. The denominator is approaching 0. And this time, we're approaching 0 from the left, or values that are negative. So we're approaching 0 through negative values, which means that this evaluates to negative infinity. So again, the 5 divided by 0, you have to realize that we're just writing that down as a placeholder. We're not saying it's 5 divided by 0. We're saying the numerator is approaching 5. We're getting closer to 5, while the denominator is getting closer to 0. That's all we mean when we write that. So that's giving us the infinity. The sign of the numerator and denominator give us the sign of the infinity. So that's where this is coming from. Are there any questions about that? Yeah.
So as long as we're doing like these kinds of problems where we have to make notation of char work that it's positive or negative infinity, do you want us to do that plus 0 or minus 0?
Yeah, I don't know, whatever makes sense to you to denote that, this is happening. I haven't really thought of a better way to denote that. But if you think of something, let me know.
I've just been doing the like 0 and plus exponent.
Okay, with the plus, yeah, so that would, if you want to write it out like this instead, like the numerator's approaching 5, denominator's approaching 0, through positive values of 0, it's kind of the same thing. I don't really care where you put that, just as long as you know that you're approaching 0 through positive or through negative values. That's one of the most crucial things when we're computing these limits. We have to know what values we're approaching 0 through. So then if we just looked at that limit, part 1 and part 2, what we're coming up with is, as I approach 0 from the right, the y values get larger and larger. So as I approach 0 from the right, the y values get larger and larger. And as I approach 0 from the left, the y values get smaller and smaller. So those two limits give us this picture. It doesn't give us the complete picture, so I'll erase this right here, but it does give us this information here and here. Everyone all right with that? Yeah.
So somebody kind of already asked this, like, in a way, but with the if you had limit or as x approaches 0 from the left like that, and then you had, instead of 5 plus x, you have negative 5, then you have a negative on top and bottom. I guess those cancel out and you're approaching from positive infinity?
Right, it would approach positive
Okay.
infinity. Again, if our numerator was approaching negative 5 in this example, the negative here and on bottom would divide out to give us a positive infinity. So really it just depends on, it's not always that when I approach 0 from the left, I approach through negative values. It really depends on the function itself. So, just backing up, this from an algebra perspective, this is what we came up with. We said, oh, hey, we know where there's a vertical asymptote. Let me just plug some points in and see where the rest of the graph is, right? So that's what we came up with through that lens, plugging in 1 and negative 1. Now, through the calculus lens, we have, it's all sort of streamlined and compact. We don't have to even look at a graph to know that this is what our work's showing us visually or graphically. Okay, how about the limit as x approaches 0 on 1 over x squared? start out with a couple of ones so we can kind of get our bearings, and then we'll look at a few different, or more involved examples, I should say. So as x approaches 0 from the right, the numerator is still approaching 1. The denominator is approaching 0, again through positive values. So we're approaching 0 through positive values, but in this function, those values are being squared. So what would our quotient approach? Positive infinity, yeah. We've got a positive over a positive. Fixed number on top, denominator's getting smaller and smaller. The quotient is getting larger and larger. I'll just put this here. Usually if it's a positive infinity, we don't write that, but just want us to be mindful of of the signs. What about as we approach, x approaches 0 from the left? Positive infinity. Numerator approaches 1. The x here approaches 0 through negative values of 0, negative values rather. But all of those values again are getting squared. So that square and that all of those negative values, that square makes all of those negative values positive. So essentially what we're looking at is this, once we square that, which again is positive infinity. So maybe I don't know a whole lot about this function based on my work, but I do know when I get closer to 0 from the right, that my function's up here. And when I get closer to 0 from the left, my function's also up here. Whatever else it happens to be doing. Do y'all have any questions? So it's kind of weird at first when you start evaluating these things. I realize for some of y'all it's been a long time since algebra or pre-calc, and in those classes you get this much exposure to something. And when you get into calculus, it's like, oh, you're supposed to remember all of that, but in reality, we don't. I do hope some of this stuff you do remember, because if you remember that stuff, you can see that what we're doing here with limits, it's just a different way to explain. It's a more precise and technical way to explain a lot of things that you've done in the past. So we really can't just talk about limits in algebra or pre-calc. But if we could start there, I think it would make the concepts of all of these things a lot easier to understand, right? Like when you first see a hole, you're like, well, how like on a piecewise function, how do I plug 3 into that function when the function doesn't even include 3, right? Stuff like that is easier explained through the sense of a limit. It's not that we're plugging 3 into the function. We're just saying that those values were getting closer and closer to 3. So those things make more sense in the sense of a limit, but alas. Okay, just some kind of note about how we're denoting this stuff in this section. So when we write n over plus 0, all we mean is the numerator is approaching some number, the denominator is approaching 0 through positive values. And then when we write some number over -0 in the sense of a limit, numerator is approaching n, denominator is approaching 0 through negative values. So that's what we mean in this section when we write that. And honestly, anytime we write something divided by something like this in the context of a limit, that's what it always means. The top is approaching this, and the bottom is approaching this. So if you want to use subscripts or superscripts here with the positive 0 and the negative 0, feel free. Again, there's not any universally agreed upon way to denote that. Is everybody okay with that notation? In the context of a limit, we've got to think about it's just approaching those things. So, like, if we know that this function 1 over x squared looks like this, close to that asymptote, how would we determine what's happening everywhere else? Like, how do we determine what's happening over here and what's happening over here, for instance? Yeah, so that's where the next section 2.5 comes in. What is the graph doing way out here? And what's the graph of the function doing way out here? So this is where we have to look at limits as x approaches negative infinity to see what our y values are doing out here. And over here, what's the limit as x approaches infinity. So that's how we would come up with another large portion of that graph. So does everyone have what they need here? Move on. So here's another example. Evaluate the limit as x approaches 2 on the given function. So as always, when we look at these limits, we might think there's a couple of things I could do here, but we're approaching 2, and the denominator is x minus 2. So initially, it could be a problem. We might be able to cancel one of those factors out, but we don't know until we start factoring the numerator. So let's factor things completely and then see what we're dealing with. Okay, so the top, we're going to factor, unfortunately, it's not going to help. So no factor of x minus 2 in the numerator. So we're just kind of stuck with that function as it is. So nothing cancels. There isn't any holes in that function. So then what do we know about this function as we approach 2? What's going to happen? It's a vertical asymptote, right? There's no way to get rid of that 0 in the denominator. So we need to compute, 1, the limit as x approaches 2 from the right on this function, and from the left as we approach 2 from the left. All right, as x approaches 2 from the right, what is the numerator approach? Yeah, the whole function would, yeah. But the numerator itself, x approaches 2, there's no issue with the numerator, is there? No, so this is 2 minus 4 times 2 minus 5. What is the denominator approaching?
Positive 0.
It's approaching 0. what values of 0 is it approaching through? Positive. We're approaching 2 from the right, or values that are slightly larger than 2. When we take any value that's slightly larger than 2 and subtract it from 2, it's always going to be a positive number. You know, sometimes, I don't know, if you draw pictures, sometimes with these limits it could help. I don't know if it's accurate for you, but we're approaching through all of these values. Any of these values in for x will result in subtracting 2 from it, so those values will always be positive. Is everybody all right with that? Are there any questions at all? So then we have up top, we have a positive 6. We have got values that are super small and positive being squared, so they're still super small and positive. Which means that limit is a positive infinity. What do you think then about the limit as x approaches 2 from the left? Okay, so because of the nature of their denominators being squared, does it really matter what values of 0 we pass through? No, because the denominator is always going to turn into something that's positive, because we're squaring that result. Oops, positive 6. So the numerators, we're approaching 2. Nothing wrong with 2 in the numerator again. So we've got a negative 2 times negative 3 in the up top, again, positive 6. This time, we're approaching 2 from the left. So here's, 1, here's 0, let's say. If I plug any of those values in for this x, all of those values, since they're smaller than 2, will be subtracted from 2, which gives us a negative in there. But again, that quantity x minus 2 is being squared, so it's still 6 over positive. Tiny values, which is still infinity. So even if we didn't know anything about that function, once we compute these limits, I'm approaching a finite number, my limit's approaching infinity. That automatically tells us that we have a vertical asymptote when x is equal to 2. Is everybody okay with that? So I would recommend when you're doing these limits to maybe, even if it doesn't ask, to just think to yourself, what is that telling me about the function? Like those limits in 2.3, when those things canceled out, we said, oh, there's a hole there at 1 comma 2/3. Here, we're saying there's a vertical asymptote at x equals to 2. So just kind of keep those things in the back of your mind, because it does matter. It is important. Are there any questions on this?
If one was approaching positive infinity, one was approaching negative infinity, you said because they're both approaching positive, your x equals 2, but which x equals then?
If both of them are approaching different infinities, we would still have a vertical asymptote. So, like, let's say for this purpose, that thing was approaching negative infinity, and the other one, as from the other direction, is approaching a positive infinity, that doesn't negate the fact that you still have an asymptote at x equals to 2. What that means is, instead of approaching this asymptote like this, in the sense of alternating those signs, that just means as I approach infinity here, and then the other one approaches infinity there. Any other questions? All right, how about this limit? So take a couple of minutes, see what that limit equals to. So the limit as x approaches 2 on this function, anyone want to share with us what you have?
Negative 1/3.
Negative 1/3? Let's just write that out. Negative 1/3. Did anybody else get negative 1/3? Okay, good. So it is negative 1/3. What does that mean about that function?
There's a hole there.
There's a hole. I'm approaching a finite number. X is approaching a finite number, so is Y. So there's a hole. So that's work that out, factoring the top and bottom. Well, the bottom's already factored, but factoring the top allows us to divide out the factor of x minus 2, which allows us to compute that limit. There questions on this? So what if we took the same function then and compute the limit as x approaches -1? On this function, what happens at -1? Notice that factor of x plus 1 didn't go away, did it? Okay, so let's just work this out. The limit as x approaches -1, and we can write this down out again. What was it? X squared minus 5x plus 6 x minus 2. So if we started off with this limit, we would do the same thing. We would factor the numerator and the denominator and see what we're actually dealing with. So in this instance, we see we're dealing with that factor on the bottom not going away. So when you get to that, I hope you recognize that, well, I've got a vertical asymptote on this function at -1. At this point, I need to look at one-sided limits. So what's the limit as x approaches -1 from the right on this function, x minus 3 over x plus 1? Okay, so let's just view it here. As x approaches -1, the numerator approaches, -1 from the right, the numerator approaches what? -4. Denominator, we know, is approaching 0. What values of 0 are we approaching through as x approaches -1 from the right? Positive? Do y'all agree with that? Here's -1. As we approach -1 from the right, we're taking all of these numbers, like -0.9, -0.99, all of those numbers are added to 1. So those end up giving us a tiny positive number. Yeah, do y'all agree? Have any questions? Okay. So we've got positive over, or negative over a positive rather. So this approaches negative infinity. So we've seen functions where we approach from either direction and the infinities are the same. They could be different. So don't always assume that they're the same, like in the sense that like a rational function like this, and don't always assume that they're different. Like seriously go through this analysis to determine what's happening. So then from the other side, -1 from the left, x minus 3 over x plus 1. Numerator still approaching -4. This time, what's the denominator approaching? 0 through negative values, yeah. So we're approaching -1 from the left, which are values that are larger than -1. When those values are added to 1, that gives us a negative small number. Okay, so like just -1.01 plus 1, that's a small negative number, yeah. So our quotient is approaching positive infinity. So now we know that the function has a hole at 2, -1/3. And what else do we know about this function? Based on these two limits, what do we know? There's a vertical asymptote where? At x equals -1, right? So it has a vertical asymptote at x equal to -1. Because as we approach -1, the function values approach infinity. Is everybody okay with the difference there? We've got, as we approach a number, the y values approach a number. That gave us the whole. As we approach this number, the y values approach a positive infinity. That's our vertical asymptote. And not only do we know we have a vertical asymptote at -1, we know the behavior on either side of that vertical asymptote. So based on that limit stuff, we know here at -1 is an asymptote. As we approach -1 from the left, the function values approach positive infinity. So -1 from the left, function values approach positive infinity. And as we approach -1 from the right, the function values approach negative infinity. So from this side. So, you know, I don't know, whatever else this function's doing, we don't know that, but we do know where those arrows are in relation to the asymptote now.
So can you remind me why we chose to approach it from the x to -1?
Yeah, so either, like in the sense that could be just a problem that was given to us, or in the sense of this problem, you know, maybe we start off with this function that's given to us, and it says, determine where the holes in the asymptotes are in that function. So we would proceed with factoring it, and say, well, this isn't the right one, sorry. We would proceed with factoring it, and saying, okay, well, this is what my function reduced to. Before I even looked at any kind of limit, right? This is what my function reduces to. I know there's a hole at 2. So then let me compute the limit to see where the y coordinate is. I also know since this one didn't go away, there's an asymptote at -1. So let me then compute the limit as we approach -1 to see what happens.
I see.
So it could manifest in different settings. Just, you could be given this limit straight up, say evaluate this limit, or you could say analyze. You could say something like analyze the rational function. Where are the holes? Where are the asymptotes?
Thank you.
You're welcome. Any other questions about this? So I do want to look at 2 more examples in this section, but we'll take a break, and then we'll finish 2.4 and start 2.5.
So if I could give them
Yeah.
Yeah, for sure.
I've got like, not this close.
Okay, one other example, well, one of the last examples, the to look at. So some of these trig functions, the reciprocals like tangent, cotangent, secant, cosecant, those limits can be analyzed the same way we're analyzing the limits on these rational type functions. I guess what I intended was for us to look at it numerically. But I think I'll skip the numerical stuff. If you want to figure out numerical stuff, I really don't want to encourage that, but I know it can be helpful to look at it numerically. I will say that your calculator mode should be in radians throughout the rest of the course. So if it's not in radians, make sure you put it in radians. So I'll just put numeric here in case you want to look at it numerically. I do definitely want to look at this analytically. And I think probably for most of us, when we see cotangent, tangent, secant, cosecant, that hopefully we're thinking about sine and cosine. So really, to know anything about tangent and all those other functions, you just need to know some information about sine and cosine, and the information about rational functions where it has zeros, where it's undefined. That's also extremely helpful. Okay, so maybe we totally forgot what cotangent looks like. That's fine. Let's think of it though in terms of sine and cosine. So that's the limit as x approaches 0. Cotangent is what?
Cosine over sine.
Cosine over sine. So rationalizing, conjugate, none of that stuff works here. As x approaches 0, what does the numerator approach? 1. Cosine of 0 is 1. What does the denominator approach? 0. Sine of 0 is 0. So it's at this point we realize that, oh, I have a vertical asymptote there when x is equal to 0. What's the behavior near the asymptote? Now we have to look at the limit from the left and from the right. So then we compute the limit as x approaches 0 from the right on cosine over sine. And from the left. So we said as we approach 0, cosine approaches 1. As we approach 0 from the right, we know, again, sine approaches 0, but what values of 0 do we approach through? Through what? Positive values? Do y'all agree? Positive values as we approach 0 from the right on the sine function? Yeah. So, you know, you might at this point try to recollect the sine function. As we approach 0 from the right along this graph, we're approaching 0 through positive values. So then that tells us that the limit as x approaches 0 from the right on cotangent is positive infinity. And the limit as we approach 0 from the left would be what? Negative infinity, right? And again, we can see that through the exact same process, approaching 0 from the left this time. We're approaching through negative numbers. time through negative numbers. So that result of the limit is negative infinity. So what we would say then, since as we approach 0, even if we just computed limit number 1, that's enough to say there's an vertical asymptote. So just that limit by itself, or limit number 2 by itself, either one by itself is enough to say there's an asymptote at x equals to 0. Whatever we would, I don't know, maybe we would just call it f of x. F of x equals cotangent of x is a vertical asymptote at x equals to 0. That's our conclusion there, and same conclusion here. So if you see tangent, secant, cosecant, just think about them in terms of sine and cosine, and we can utilize the same reasoning, I guess, to evaluate those. Are there any questions on that? Yeah.
Since they're both approaching from both, or since it's approaching from both directions, like just on the graph, like how is that approaching infinity? It looks like they're both coming in to like 0, 0.
Okay, yeah, so just be careful. We're using the graph of sine to analyze the denominator. What values of 0 are we approaching through? But if we looked at the graph of cotangent, we know that as I approach 0 from the right, cotangent approaches infinity. So on the graph of cotangent, we would have this, and I approach 0 from the left, cotangent approaches negative infinity. So when we looked at the graph of cotangent, we would have an arrow here and here, so we approach it from the left or the right.
Okay.
But that was just the graph for sine x to help us analyze the quotient. So this part is only for this part on the bottom.
Okay, that makes sense.
Okay. Yeah. So we'll go ahead and put the graph of cotangent in there. There's kind of what all we've determined was close to 0, however. So we know that it's up here, and over here we know it's down here. Any other questions? So the next concept we're going to look at builds off of this. It's closely related to the ideas we're discussing, although it is more prominent in Chapter 3 when we start looking at derivatives than it is here. But since we're able to discuss it now, we can, and we will. So we're given the cube root of x, and if there are a few things we're going to do. First, we want to find the slope of the secant line through the points 0, 0, and the point h, comma, f of h. So the slope of the secant line is just the slope connecting those 2 points on that function. So, think about this as x1, y1. This is x2, this is y2. So what is the slope of the secant line?
would be h minus 0 over fh minus 0?
Close, we want to keep them lined up. You just had one of them mixed up. But yeah, that's all we're doing, right? Slope of those, the y2 minus y1 over x2 minus x1. So we see that's just f of h over h. Do we know f of h? Is what?
Cube root of h.
Yeah. F of x is the cube root of x. F of h is the cube root of h. Oops. And then we can simplify that. H to the 1/3 divided by h gives us what?
H to the negative 2/3.
Yeah, so remember subtract their exponents, h to the negative 2/3. Which you'll remember is the same as 1 over h to the positive 2/3. Which we could write as 1 over the cube root of h squared. So we've computed the slope of the secant line for any h value. And we started off with the actual point on x cubed 0, 0 at the origin. And then we said, well, if I step away from 0 by any distance, h, what's the resulting slope of that secant line? So again, we have a generic secant line for any h. For any distance we are from an x value of 0, we can compute the slope of the secant line. So we'll look at the graph in a minute, but if this is the graph and this is the origin, we're saying, all right, let's compute the slope of the secant line that runs through this point. And maybe that's h equals to 1, gives us the second point, right? And then we say, well, what if h is a half? Then we have these 2 points, that's the slope of the secant line. If h is equal to 1/10, then the slope of the secant line is here. But all the while, we have a function of h to just plug in that distance from 0 to compute all of these slopes. Does that make sense? So the slope of any of those secant lines, as long as we know the distance away from 0, is plugged in h equals 2 and 1 over the cube root of h squared. So there's our secant line, the slope of our secant line, rather. And then we're asked to calculate the slope of the secant as h approaches 0 from the right and the left, and interpret the results. So we're asked to calculate, 1, the limit as h approaches 0 on the slope of our secant line, found in part A. So we're calculating the limit as h approaches 0 from the right on 1 over the cube root of h squared. And the limit, sorry, from the right. the limit as h approaches 0 from the left. That's what we're asked to compute, and then we're asked to also interpret the results. So whatever that limit equal, those limits equal to, what are we computing here?
Instantaneous rate of change.
The instantaneous rate of change, right? So anytime we take a limit on the slope of the secant line, we end up with a slope of a tangent line. The way we looked at it with a particular example from 2.1 was we looked at average rates of change, right, which are the slope of the secant lines, and then we put a limit on the average rate of change, or average velocity. Once we put a limit on the average velocity, that gave us the instantaneous velocity. Do y'all remember doing that? So whatever this equals to, and whatever this equals to, it's giving us the slope of a tangent line. So that's what we're going to use to interpret our results. Whatever we're calculating is the slope of our tangent line. Specifically, the slope of our tangent line at what point? So let's just say this. We are calculating the slope of the tangent line on the given function at what location?
Zero.
At where?
0.
Right, at the point, or at the x value 0, which is the point 0, 0. So remember from part A, we started from 0, 0, and we went to h, comma, f of h. If, as we're computing here, if h goes to 0, then this is 0 for h, and this is f of 0. And f evaluated at 0 is just 0 to the 1/3. So that's 0, 0. So whatever our result is on 1 and 2, that's saying on the function cube root of x at the origin, that's the slope of the tangent line that we're calculating in part 1 and part 2. Does that make sense? Do y'all have any questions on that? So let's compute these limits. In other words, compute the slope of the tangent line on that function at the origin. So as h approaches 0 from the right, what is 1 over the cube root of h squared approach? Positive infinity, what do y'all think? Is that positive infinity? The numerator approaches 1. We can clearly see the denominator approaching 0 through what values of 0? Well, we're to the right of 0, we're squaring those values, and then we're taking the cube root of those values. So that limit is infinity. So now we're looking at infinite limits in the sense that they're generated directly from a slope of a certain line, as opposed to looking at limits at infinity telling us we have a vertical asymptote, okay? the sense of a vertical asymptote here is if we only looking at the function 1 over the cube root of h squared as the function, that function, this function here, has a vertical asymptote when h is equal to 0. That's still true, but we're looking at this in a slightly different sense because we know that in the context of this problem, where that function of h actually came from was describing the slope of all of these secant lines. As h approaches 0 from the left, what does that function approach? Negative infinity? What do y'all think? Or positive. So the numerator approaches 1. The denominator we approach through negative values. Those negative values are getting squared. So let's just write this out. Negative values being squared, and then we're taking the cube root of them. So since that square is there, it's still infinity. I'll make that smaller. So we've got the slope of our secant line described as 1 over the cube root of h squared. We're applying a limit to that, which automatically tells us we're describing the slope of a tangent line. So the slope of the tangent line on the function x to the 1/3, as we approach 0 from the left and from the right, the slope of that tangent line is infinite. So what does it mean for a line to have an infinite slope? What kind of line is that? A vertical line is the only line that has an infinite slope. Both limits are, let's say both limits, and just note here that the limits are describing, as we said, the slope of the tangent line. So those things both are infinite. That is, this function, where we constructed where we measured the slope of the tangent line at, f of x equals x, the cube root of x at 0, 0, has a vertical tangent. So here's the cube root of x. So what we've computed in part 1, we said, I've got the slope of the secant line that connects any 2 points from 0 to wherever as a function of h. And then I said, what happens if I allow this point, in part B, we computed what happens if I allow this point to approach this point. And so then we started computing those and saw that this slope became infinitely large. Remember, in the sense of a tangent line, we're just touching at a point. So if this is a tangent line touching at that point, and then maybe we have a tangent line here, and then a tangent line here, and a tangent line here. So we see those tangent lines, they all have a positive slope, but they're getting more and more vertical as we approach the point along the function at the origin. You see that? So they're getting more and more vertical. Just imagine like your pencil riding along this slope. As it gets more and more towards the origin, it starts to become vertical, and that's what the work that we've shown tells us. Same thing with the negative direction. Here's a tangent line here at this point. Here's one at this point. Another one at this point, and this point. So again, just imagine your pencil riding along the curve. That's the slope of the tangent line. As we get towards the origin, it's vertical. So as h approaches 0 from the right, and as h approaches 0 from the left, those came out to be positive infinity. So that's our vertical tangent. Do you have any questions on that?
Is it possible to interpret a negative infinity as a vertical tangent line as well?
Right, yeah. So negative infinity could be interpreted as a vertical tangent line as well, because we're just saying that that slope is infinite. You'd have to look at it in terms of the magnitude, because it, like to have a negative infinity slope versus a positive infinity slope still means the thing's vertical. Typically, when those things are stated, though, it's stated in terms of the absolute value of the function, just to avoid that confusion. So we always just talk about the magnitude of it being extremely large. We don't care what direction it's headed. So again, this will show up in Chapter 3 once we start talking about derivatives or slopes of tangent lines. But it's definitely related to the limits at infinity. Any other questions on that example? So then we'll start 2.5. As we mentioned at the beginning of 2.4, limits at infinity in 2.5, they describe any behavior or where we have horizontal asymptotes. Because the nature of a limit at infinity is we're taking the independent variable and letting it go to infinity or negative infinity. We're saying what's happening over here at this end and at this end. And some specific applications are, populations that evolve over time. Maybe you've got a function that models the spread of an epidemic, and you want to know, does that epidemic keep going, approach infinity, or does the epidemic die out, or it approaches some finite number of infected people? So that's kind of with growth and steady state as well. So here again is a visual definition, I guess, of what we mean when we say limit at infinity. So that's the figure that corresponds to this definition. Now you'll notice in this definition that there's two limits at infinity. One they're calling capital L, the other they're calling capital M, because in general, depending on what kind of function we're talking about, as we saw with inverse tangent, for instance, you can have more than one horizontal asymptote. So in the sense of our definition below, it's saying that on this function, as x approaches infinity, f of x approaches L, and as x approaches negative infinity, f of x approaches M. But in any case, if that's the situation, if x approaches infinity or negative infinity, then you've got a horizontal asymptote at L or horizontal asymptote at M. So when we approach a finite number and the limit is infinite, that's a vertical asymptote. When we approach infinity and the limit is finite, that's a horizontal asymptote. So we kind of interchange the role of x and y with these two. A similar way to look at these things, if we have a quotient like a over b, and we know that the quotient is approaching 0, the quotient is getting smaller and smaller, then what that means is the denominator has to be getting larger and larger. So again, it's sort of the flip side of what we just talked about. What we just talked about is if a is fixed and b gets larger and larger, your quotient gets smaller and smaller. But if b gets larger and larger, well, I just said that. But if b gets smaller and smaller, then our quotient gets larger and larger. Okay? So we're looking at this kind of situation here with limits at infinity. Okay. We asked this question last time, but is it possible on some function for the limit as x approaches infinity to be infinite itself? Yes. What kind of functions did we mention there?
Polynomials.
Polynomials, right. I'll just say on polynomials, for example. Maybe you think about x squared as a polynomial. So as we go further and further out in this direction, the y values get larger and larger in this direction. Similarly, in the negative direction, as we go further and further out, the y values also grow towards positive. But then we maybe remember other instances of polynomials where it just kind of depends on what function we're dealing with. So maybe we have this polynomial. See, the nature of the end behavior is slightly different, right? Because as x approaches positive infinity, y values approach positive infinity. As x approaches negative infinity, the y values approach negative infinity. So in this section, if you can remember, stuff we did with polynomials, it can be very helpful to kind of reason our way through some of this stuff. So as far as polynomials are concerned, how did we determine where to put the arrowheads before we even looked at limits? There was a specific name for the test to determine if I'm talking about a polynomial function, where do the arrowheads go? Are they both up here? Are they both down here? Is one up, one down? Or is one up here and one down here? How do we determine that? Anybody remember the name? So parent functions were with like graphical transformations or function transformations.
Well, isn't it dependent on whether or not your exponent is even or odd?
Right. So it depends on whether the exponent, we'll make that a little more precise, but that's, you're on the right track. So here, I will say limits at infinity on our polynomials. Remember, limits at infinity determine end behavior. And what I'm asking is how, before limits, did we determine end behavior? On or with polynomial functions.
Remember looking at the degrees?
What is it?
By looking at the degrees.
The degree, right. Do y'all remember the degree of the polynomial? That's what you refer to, the exponent. The highest exponent on the polynomial was one of the things we had to look at to determine where the arrows were placed. There was another thing we had to look at, though.
Horizontal line or something.
Not quite. The degree and what else affects the shape?
The jumps.
The coefficient. The coefficient on the x with the highest power. So right, if this were positive 1x squared, then it looks like this. But if it's negative 1x squared, it looks like this. Y'all remember all that? Maybe not. What we called that the leading term test. Does that sound familiar? The leading term test. We use the leading term test. And so the leading term of a polynomial depends on two things. It depends on the degree. So we'll say even degree and odd degree. And then our leading coefficient we called a sub n. So if our leading coefficient is positive, we had an end behavior, a different end behavior if the leading coefficient were negative. And just to remind you, the general definition of a polynomial was this. So depending on which two things happen together, determined where the arrowheads or the end behavior of polynomials went. So when we think about even degree and a positive coefficient, just think about positive x squared, where its arrows, they both point up like this. Even degree with a negative leading coefficient, think about negative x squared. Its arrows point down. An odd degree with a positive coefficient, think about positive x squared, where its arrows are down then up. Odd degree, negative leading coefficient, just think of negative x cubed, where the arrows are up then down. You know, and you had the function was, of course, doing stuff in between. So usually they were like dots or squiggles. But we're primarily only thinking of the end behavior because we're talking about limits at infinity. So we're only concerned at this moment where the arrows go on these types of functions. So I'm just curious, who remembers that? Raise your hand if you remember that. Okay, fair enough. And so now with limits in place, why does that test valid? Why does that test work the way it works? So, for example, if I had, let's say, negative 3x to the 5th plus 2x cubed plus x squared minus 15x plus 30. The questions that were typically traditional with polynomials in prior math courses would be, what is the end behavior? The end behavior of f of x. And then, they might have said something like, draw it. So with that in mind, you said, all right, well, where's the highest power of x? Here's the highest power of x. This whole thing right there is my leading term. And we said all I need to know about the end behavior is based off of the leading term. It's an odd degree with a negative leading coefficient. So an odd degree with a negative leading coefficient, the arrows are up and then down. So we said, well, I know way over here the graph is up here, and then way over here the graph is down here. And we didn't fill in the rest because we didn't know where the x and y intercepts were. So why are we able to do that? When we're talking about the end behavior, why are we able to ignore everything else and only look at the leading term? So how or why?
As your x values get larger and larger in either positive or negative directions, the variation between x to the 5th is much greater than x to the cubed or x squared. So the difference grows wider, therefore the leading coefficient, or the leading term, is the most pronounced value.
Right, yeah, exactly right. So the leading term is the most pronounced value in the sense that end behavior means x is going where? To infinity or negative infinity, right? So as x gets super large, like if I'm talking about 1 billion to the 5th power and then I'm adding 1 billion to the 3rd power, what is that? It's basically still 1 billion to the 5th power, isn't it? So as x grows large without bound, those lesser terms are completely meaningless because the leading term is growing so large, so fast, that everything else is really inconsequential to that leading term. So that's the reason that worked, because the end behavior, again, either x is approaching positive or negative infinity. I guess we could say because when x approaches positive or negative infinity, the lesser terms again, we're only speaking strictly in the sense that x is growing larger and larger. If x is really small, then of course all of those other terms matter. We're just saying that as x gets larger and larger and larger and keeps doing so, that those terms that are not leading terms start adding less and less to the overall value. Does that make sense? Again, if it doesn't quite sit well with you, then take like x to the 5th plus x to the 3rd and just plug in really large values for that, and you'll see that it's always going to be closer. As you get larger, it's always going to be closer to x to the 5th than it is x to the 3rd. Whatever number you're cubing and raising to the 5th power. Okay? So this is how we compute limits on polynomials. Limits at infinity on polynomials. We'll write this down next time, but limits at infinity on any polynomial function, all you have to do to compute it is to look at the leading term. And then we'll take that notion and build it or work with it when we start looking at rational functions as well. We'll see y'all. Have a good weekend.
So that engineering homework is like. Did you actually read the chapter?
No. Okay, so like, you can, for every other function, I could help you. Do you like have a rule to help you with that? 6 of the 7 functions.
Really?
Yeah.
Yeah.
That's certain features.
Oh, really?
A lot. He was with me when I was doing it.
Oh, really?
No, those are available. Like, I can look at those, but I took pictures of the right ones.
Oh,
So I went back through and made sure that
All right.
I didn't get them wrong. Yeah, I'll be like, look, all of these 7 tries work for one question.
Yeah.
I'm just gonna keep
I
trying.
mean, except for that first
combination.
one where you get like a 40.
It's because I didn't read it.
I do that too, and I forget them right.